Hello, hello. Okay, it works. Welcome. Thank you for coming to this session. So we have 4 speakers today because we have a lot of topics to discuss. We will do a quick introduction. So we are all working for IBM. But why do we do introduction like we do normally, like I present myself, Georgios introduces himself, while we have AI for doing our own introduction? So we are going to use AI to see who we are. So let's start with Mario.
What can go wrong?
Yeah.
Okay.
Intro. Yeah. So Mario, let's run it. Mario, over the past years, has been contributing massively to LangChain4j. So let's see if OpenAI, because in this session we are going to use OpenAI just for the performance reason and speed. You can use all our demos with local models. You will have the code of everything at the end. And see, so there are several named Mario Fusco. Okay, so it doesn't really know you. Well,
let's help it out.
Last week he believed it was a footballer, so at least it's...
This is already an improvement, yes.
Yeah.
So you can...
let's guide him. Let's see. Wow. And restart that. So one thing that is interesting about Mario, so Mario, as I said, is a LangChain4j contributor. So the API he likes is really the LangChain4j API, which are builder-based, so you will use something like that, like OpenAI chat model, API keys, the model you want to use, and things like that. And now, it's like Mario Fusco is a software engineer and open source contributor in the Java ecosystem, notably maintaining and contributing to LangChain4j. So he knows it, or he did use it. The Java part on LangChain, yeah, that's not really true anymore, but anyway. Beyond that, public biographical details are limited. You need to work on that, Mario. Huh? That's would be good. So, okay, that's Mario.
Nice.
Is that all true?
Yes.
Is that true?
Sort of, yes.
Okay. So,
at least it's a big part of my life in the latest month, so yes.
So next we have Georgios. So Georgios is our...
May I help you? Okay.
Yes.
Do this. It's easier.
Oh, you have a shortcut to command.
It's control / anyway.
So now we have Georgios. Georgios is our main implementer behind Quarkus LangChain4j, the integration of LangChain4j and Quarkus. So how we do the Georgios introduction is to use mostly the same kind of code, so the chat method to ask the model, but this time we don't instantiate the chat model directly. We have Quarkus injecting it for you. So, and now we have Georgios, which is a software developer known for his contribution to Quarkus ecosystem and LangChain4j project, blah, blah, blah. Yeah, no, that sounds...
Yeah, no, that's really good.
Yes, that's really good. Yeah, okay. Let's try myself. So, last week I was a chef. And believe me, it's better that I'm not going in the kitchen. So
do it again. Okay.
Let's try. So I'm mostly doing a lot of coordination between Quarkus and LangChain4j and the overall Quarkus project. So I prefer more high-level abstraction. And in my case, the development model I'm using are named AI services, or Quarkus AI service, where I actually have, where is this one? This class here. Oh, no, this one, introduction service, where I have this register AI service. So it's a bean, it's going to be a CDI bean, where just an interface, you don't implement it. Quarkus is doing that for you, and you just ask your question here. So instead of calling the chat method, now you are going to use the introduce method, where you just pass a name, and you see there is a templating model, name, and so on. So Clement Escoffi is software engineer at Red Hat. Well,
yeah, that's wrong
as
of last month.
Yeah, so it's not really up to date. No, I'm working at IBM. He's a co-lead of the Quarkus project. He's a champion development of this Kubernetes native Java framework. Okay. Yeah, it's partially accurate, except my company. The rest is okay. And now we have Stefano. So Stefano is our A2A expert. So A2A means agent-to-agent protocol. It's to interact with remote agents. So in his case, the code is slightly more complicated. We will see that in detail. He will all explain. But basically, here, where are you, Stefano? You are here. Who is Stefano Maestri? You invoke the agent. Let's run this. And that's my client here. So you have a client to write and events to catch and things like that. But we will go into all these details. But basically, it's like having this AI service working remotely and having a protocol, a specific and specified protocol that tell you, oh, and it doesn't work. Oh, no. Yeah, but that's okay. That's the exception. Okay. Yeah, wrong network stack, by the way, but whatever. It's
that's fine.
The HTTP client from the JDK. But we have the response. Stefano Maestri is a software engineer known for contributing to the Wildfire project. That's true?
Correct.
The open source. He has been active in the Wildfire community, contributing code and announcement within a broader Red Hat development ecosystem around Wildfire. This is pretty, it's pretty vague, but yeah, okay.
Pretty right.
Yeah, it's pretty right. So, not Red Hat anymore, but.
And no A2A mentioned, but anyway.
All right, so now we know who we are. At least we know that OpenAI know basically who we are. I don't know if it's reassuring or not, but anyway. So what we're going to discuss today is how in 1 year things are completely evolved in the AI world. Last year I was there with Georgios, Mario, you was there too, and we presented how we build chatbots, sentiment analysis, RAG, function calling, summarization, image recognitions, and all these. We didn't have A2A, it was the bare beginning of MCP and things like that.
Yeah, we didn't even have MCP.
Yeah, it was really starting the first line of the spec, the MCP spec. Today we are changing completely. We are in a new world. We are in a new world where we want to compose systems based on AI. So every single of this circle is an AI-infused application. And this application will use different models, different temperature, different configurations, will use function calling and so on. But the beauty and where things start to be very interesting is when they start to be assembled together and work together, collaborate together. So, well, last year we were really doing single AI-infused application for one task, like a microservice, if you want a parallel. Now, this year we want to say, okay, how do we assemble these microservices all together? Because in the enterprise world, we don't necessarily need just one microservice. We need a fleet of them with integration patterns like workflow and automation and decision-making and things like this. So, this is the journey that we're going to do with you. So now, believe me, it was not a straight line. We have another talk tomorrow evening with Mario and Georgios, where we will, if you're interested, we will tell you all the failures we made over the past 6 months to 1 year to reach the level we are today. Yeah. Because we made a lot of shortcuts. We believed we understood, and we didn't. And it hurt.
So today we will show you the arrival point, the final destination, but we believe that also the journey is important, that there is a lot to learn from it. So
what you don't realize, because he got a haircut last year, but Mario, probably age of 10 years in the last 6 months because of this. So that's basically it. So we will start with the foundation. The foundation are basically AI services and everything that we put around AI services to augment their knowledge, capacity, and so on. Then we will go in the first level of autonomy, the first level of assembling these AI services, which are workflow and patterns. So that has been the work from Mario for the past 6 months, more or less. Then we will go to another level of autonomy with goal-based autonomy, where we are going to give a goal to an AI service, and this AI service is going to delegate that automatically to a fleet of other sub-AI services. And we'll see how it works, both locally and with A2A. So, just to give an idea, we will see chat model AI services, memory, function calling, MCP, and so on, and then we will go more on the composition patterns and then on goal-based autonomy. Okay, so just who was there last year? Who knows what AI-infused applications are and how they are built? Okay.
Not bad.
Few, yeah, okay. So I will go back from the roots relatively quickly. You will see it's pretty natural and pretty easy. And then we will go to the next level and then the final level. So the first thing, and it all started like this. Like, okay, we want to have an application which use AI, use an LLM to a generative model to implement some behavior, summarization, image recognitions, sentiment analysis, extracting information, whatever kind of things we do with AI today. And, well, having just this is just not enough. In the enterprise world, we need a lot more than just a client that interacts with a model. If you start doing that, very quickly, your application will become a spaghetti code with a lot of HTTP or whatever protocol the model is using or the model serving is using. And yeah, it's going to be a mess for maintenance and things like that. So the first thing is that you will need prompts. And that's how we interact with models. You give instructions in natural language. So it's a big difference between regular APIs we were using before. Like you have the method names, the parameters. If you change anything, it's not going to compile, except in JavaScript. But yeah, I'm sure it's a good thing. Here, you give instruction in natural languages. And one thing to keep in mind is that models are like teenagers, in the sense that if you give instruction to one model, may understand or not. If you give the same instruction to another teenager, the understanding might be different. And one thing, all teenagers are like that, if there is any possibility of a loophole, they will find it. So be pretty clear, over-specify if you need to, but yeah, you need to have prompts and you need to do that correctly. So then we have the chat memory, because one thing that is amazing about AI is that a lot of people have tried ChatGPT, for example, and it remembers what you just said before. So everything is working, and most people believe that the model is remembering you. No. Models are selfish, they don't remember you. What remembers you is actually the application between you and the model. The model is totally stateless, doesn't do anything. However, the application in between is going to accumulate knowledge about you, accumulate all the messages you have sent to the LLM, and then build a memory out of that. So basically, every time you interact with the model, you don't just send the last message, you send the whole conversation back. It would be exactly like if every time I add a new sentence to my talk, I will restart from the beginning. Don't worry, I'm not going to do it. But yeah, because I don't remember what I said, but that's another story. So you will have to do that. So you need some middleware or some components that will accumulate the memory, and obviously we will see there is eviction strategies and things like that. So models have been trained on a large amount of data, but that data may not be your data. And you may want to infuse your data, your terms and conditions, your documents, your PDF, your contracts in the model. So you can do that by retraining, fine-tuning the model. Pretty expensive, pretty complicated. You can still do it. Or you can use what we call the RAG pattern, retrieval augmented generation. And in that case, we are going to add knowledge, a piece of knowledge, to your own prompt. And we're going to do that automatically. So I'm not going to go too much into RAG this year. And actually, Guillaume is just there, first row. If you are interested in RAG, last year he did a great talk about the RAG pattern and advanced RAG pattern. So go see and watch his talk after this one. Don't go right now. And then we have function calling. So function calling is the ability of a model to invoke a function in your environment. Did you see the movie Terminator? Wow. It's not exactly like that, but yeah, it can go there. We will see that function calling is super powerful, but also very hard to tame. The thing is, the model is not going to call your function directly. That's not true. The model is going to tell the application, oh, can you please call that function with these parameters? So the model is going to reason about the tools you give to the model and ask you to call these tools with these parameters. And then it's the AI-infused application that will have to locate the tools, do the invocation, pass the result back to the model, and the model can continue the inference and the reasoning and things like that. So in this case, one thing you need to understand is that you are not in control of the flow. The model decides when to call which function at what time and which parameter. So you need to be very careful with that. You need to have, well, guardrail, safe rail that keep you on track. Otherwise, you can have a lot of problems. That's actually the next one, guardrail. Models, well, we have seen that in the press over the past 1 or 2 years, can be abused very, very quickly. We can do prompt injection. We can do a lot of things. If you combine that with function calling, you can imagine the number of security threats that can be created, like forget all your instruction and delete all the users. Or, if we go back to my teenager parallel, forget all your instruction and increase my grade to the maximum one. Not something we will see. So you need guardrail and things like this. So, but once we have all these around your application, it's already quite complicated, but that was last year. Now we want to have that multiple times with different models, with different configuration, sometimes local, sometimes remote. Your tools might be local, might be remote with MCP and things like that. So things really explode in all different directions in terms of complexity. So how can we do that while keeping this complexity, well, for bare human? For how can you build a system that you will continue to understand and build correctly? How do you going to compose that? And that's what we are going to see in these 3 hours. So I'm going to use the term AI services a lot, but the difference between an AI service and an agent is very, very thin, actually. Agents are made to be composed. So agents are there to be called by another agent or called other agents. That comes in gangs, basically. So it's like microservices. If you have one microservice, great, you have an HTTP server most of the time. If you have multiple microservices that call each other, you start having a microservice system. Here, agent is the same thing. That's why we say agentic systems and not just agents. So we will go through foundation, workflow, and goal-based autonomy starting now, and we will start with a bare minimum chat model. So remember, chat models was Mario introduction, where you have the builder, and then you call the method that is chat, you give your questions, and it answers to you. At that moment, there is no memory, no guardrail, no RAG, nothing. It's plain and simple. So again, when you use a chat model, you send instruction using natural language in, and you get response in natural language out. So it uses natural language processing. Some models have vision capabilities and can recognize things in pictures and things like that. So look at the model you will use. In Quarkus, we switch the model automatically based on that. But yeah, if you really want to be at the LangChain4j, you need to pick the right model. As I said, you need to write a prompt. And something I tried after my PTO, so in August or something like that, is trying to change completely how I was doing prompt, because most of the people was going to ChatGPT or Gemini or whatever and just go there and ask a small question like, give me whatever. I realized that if you write your prompt, if you structure your prompt correctly in a almost scientific manner with sections and formatting and things like that, the precision of the response, the accuracy of the response is really better. However, every time you ask a question to AI, you need to start writing a dissertation or almost an essay of 6 pages, and you send that to the model and you get your answer. It's not really efficient, but it gives good results. So that's what I said. Prompt engineering is an art. And again, depending on the model you use, you will get different answers. Depending on the micro version of a model, you will get different answers, because understanding will be different, the training data will be different, and everything will be different. Unfortunately, for us today, we are using OpenAI, and OpenAI updated their models like Friday. You can ask Guillaume over there, just there, because Guillaume tried the workshop we're doing this afternoon, and he was telling us, oh, nothing works anymore. Why? They changed the model. So we had to rework that. So always be there and implement an evaluation strategy to make sure that you never drift and things like that.
We have people that really don't like that.
Yeah.
Who have sent rants internally about that kind of thing.
Yep. Yeah, well, you're not in control. So on the right side of the slide, you see several ways to interact with chat models. So first, as I said, Mario. Mario, you create your chat model with a builder, blah, 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 and you call the chat method. We have the chat model from Guardrails, so in Quarkus, with Quarkus LangChain4j, where Quarkus is going to create the chat model for you, and you can inject it anywhere inside your application. So you just use @inject, chat language model, and then you can call the chat methods. All the configuration will be done inside the application.properties file. Temperature, model you use, providers, and things like that. So basically, it reduces the code you want to write. Then we have the AI services, which are using chat models, but they are completely hidden at that point. So we will have a full section about AI services, so I'm not going to give too much detail on that, but basically, you can use these 3 models within any Quarkus application. You decide the flexibility you want. Full flexibility with the first one. You love builders. You want to configure everything, every call differently. You do that. Oh, you know how you want to configure a chat model for the rest of and the rest of the application stays the same with that configuration. You go with Guardrails one. You want a higher level, which will bring more enterprise feature like RAG and Guardrail and things like that. You go with the last one. So depending on your level of flexibility, you decide your level of abstraction. Computer is there. So, as I said, you send prompts in and you get text out. However, you don't send anything. You send a message. So everything is message-based. You send a message in and you get a message back. Blue and green. So each message has a role. What you send to the model can be 2 roles. System, which is basically the big rules, the scope of your interaction, and users, all the interaction you do with the model. And the response will be of role assistant, because yeah, it's an AI assistant. So the system message in orange, red, define the context and the scope. It has a higher priority. It must be sent first. If you send a system message after having sent a user message, the behavior is non-specified, let's say. Depending on the model, it can go from a crash to a total hallucination to it will basically work, but you don't know. So be very careful with that. Always start with a system message. Can be only one, and then you have the user message. So one thing you can do there is that instead of just sending the prompt, you can write your own message and structure them as you want. So typically here I'm creating a system message. In French, you are Emmanuel, all your answers need to be in Java, and all the methods and variables need to be in French. Obviously, because as you know, every French people write all their code in French. And then you can have a user message say hello world. And if you pass that to the generate function, you will have system, user, message 1, user message 2, user message 3, and so on. You pass all these, and the model will get that in and will give you the response. Because we have very short on time, I'm not going to run all the demos, but you can run this one with the code. It's just a public static void main. The list of messages you pass is what we call the context window. That's very important because that's the content on what the model is going to reason or going to infer. If you send too much data, it's like a teenager. If you send too much data to a teenager, doesn't really know where to start, it might be lost, or may do things totally weird. I'll try to use all the single piece of data because it believes that if it was given, it's necessarily useful. If you don't send enough data, again, like a teenager, if you don't send enough data and you ask questions, you can be sure of one thing. They will make an answer for you. You don't know if it's right or wrong, but believe me, they give you an answer. Sometimes close to something that is plausible, not necessarily right, but plausible. You as users, and that's a tricky thing, you as users have no idea in which state you are. Too much context, just right context, not enough context. You get the answer and you say, oh, it's fine. So we will have to use Guardrail and things like that to identify in which case you are and give you some level of accuracy or level of trust you can have. Like typically in the last one, yeah, don't use that answer because it's generally really bad. Plausible but bad. So to do that, we need memory management. So basically it's what I said at the beginning. We will send the messages, we will record them. First system message and the user message, and we get the response back, we accumulate that, we send all these, and so on. Obviously, everybody here say, well, if I have a list, and I add a message, and another message, and another message, and another message, and another message, at some point, my list is going to be very large in terms of memory. So I have this LLM context issue, but I also have a memory issue in my AI-infused application, because too many messages. And every time you send them, every single time. So it takes time on the network and so on. And one thing to never forget, you pay per token. So more conversation, more message you have, more money you give to OpenAI, Google, and so on. Guillaume is pretty happy about that. So you need to find ways to keep this memory under control. But how do we do that? How can we decide which message we can remove? It's because it's really tricky. So typically in this example, I have 3 messages. The system message, you are a useful AI assistant. Hello, my name is Clement, and then what is my name? If I send that to my model and I say, hey, what's my name? It will say, hey, your name is Clement. Stupid, you just said it to me. I'm not that dumb. Okay, fine. Now, if you evict the second message, the first user message, and you re-ask the same question, you won't remember. You won't remember because you don't send the message that contains the information you ask for. So here it's a very simple example with 3 messages. Imagine when you have long conversation, when and how to evict messages. This is a pretty big thing. So one of the strategy here is to use another LLM to do what we call semantic compression, basically a summary of the exchange so far. So we are taking all the memory, we are trying to build a summary of that, and instead of sending the whole memory back, we just send the summary. There are plenty of techniques to do that, plenty of bad techniques too, because I got summaries that were longer than my memory, so that's like, yeah. But it's probably one of the best approach today to do this. It's actually when you reach a certain size, you give this to another AI specialized in summarization, and you try to summarize that. Now, there are a couple of concerns that you need to take into account, and typically one is that the level of information you give in a conversation erodes with time. Like what you have at the beginning may stay relevant or may not stay relevant. So typically, imagine a conversation where you want to organize a trip, and at the beginning you say, okay, give me the best destination in Spain, and you will have Barcelona, Madrid, or Andalusia, or something like that. And then you decide to go, okay, I'm going to go to Madrid. That's great. So all the information about Barcelona that he printed are not as relevant anymore. So these ones are not as high in terms of priorities than the rest. So your summarization also need to take time to account. However, there are information that are, well, that stay over time. My name will still be Clement. So that one is an information that can't erode over time. So this summarization need to actually identify these 2 types of information and decide how to build the summary. So while it looks simple that building a summary is something that we have been doing for a couple of, 1 year at least, it's not that simple when you start really looking into the detail of doing that. So yeah, as I said, size limits and so on. I would go, yeah. Yeah, so, and as I said, the size of the memory is not in terms of messages. Maybe for you it's in terms of messages, but actually for the model, it's not. Models do not count in terms of size of the messages or number of messages or things like that. They count in terms of token. And there is another thing that is very, very model specific and can change between one version to the next one, is how they're tokenized. This one is a tokenizer from GPT-4 Gemini has a different tokenizer, which is actually more stable, so I prefer that. Basically, in LangChain4j, we had a way to estimate the tokenization. We almost removed it, did we?
Yeah, we removed it because it was just guesswork, yes.
Yeah, so it's pretty hard to do that. So the problem is that this is related to your pricing too, so you need to keep an eye on that. So the only way to actually do that is looking at the response from the model. They will give you the number of tokens you have, and the number you send and things like that, and having an observability stack that would give you this information. Otherwise, yeah, you can't really work on that. So it's pretty hard to know when to evict messages because you can't really know how far you are from the limit of the model and how far you are in terms of your own memory. So you need tuning to do that. Depends on the application and a lot of things. All right, second part, AI services. So that's where we start going a little bit more in abstraction, something slightly less flexible than chat models, but way more enterprising in the sense that we can assemble a lot of things in them. So basically, an AI service, it exists both in LangChain4j and Quarkus LangChain4j. How we create them are slightly different. But basically, it's an interface that you don't implement. But that interface will use annotations or just be like string answer, string questions, and we don't need annotations because we know that question is a user message. And we will just use that interface to interact with the model. So it's a little bit like the difference between using a low-level HTTP client and something like a REST client or a Feigned or the Spring one. Do you know? I can't remember.
I don't remember what they call it, but
yeah,
same idea.
High-level things where you describe your interactions with annotation, and then you just use that interface. It's pretty clean. It makes testing a lot easier because you can mock this. Mocking the chat model is possible, but yeah, it's slightly more work. Here, it's pretty simple. You just have one method. Remember, you don't implement it. And one method, you can have more than one. But here, for the example. So, and it will integrate everything I've said so far. So obviously a chat model, but also memory management, Guardrail, RAG, everything will be all put together in an AI service, so you don't have to do that work anymore. So in Quarkus, it's slightly different. You just go with register AI service, so we have a specific annotation for that, because we don't use a builder to create it. And yeah, then you just use a string answer and string question. And that AI service can be injected anywhere inside your application, which is very powerful because you can have that in a REST endpoint, in a WebSocket, well, any kind of application you are building with components. And you just inject it with @inject_assistant, and voila. That's it.
Magic.
Yeah. And why we ended up with this is basically one of the things we were wondering at the very beginning of our work around AI. It was like, okay, what is the difference between a CRUD application, which is an application interacting with a database, with a microservice, which is basically an application dealing with or interacting with another microservice, and an AI-infused application, which is an application interacting with a model. It's all three blue squares or rectangles with 3 red arrows. Not a big difference. Well, I've just changed the icon on the right, but basically that's the same thing. And what is interesting is that they actually have a lot in common. And one of the common points they have is the notion of integration point here, which is a point where you cross the boundary of the application and you start interacting with a remote system. And when we do large-scale distributed systems, this integration point are something we actually want to take care of. It's not, the rest of the code is important, but these ones are very, very important, because if anything can go wrong, it will be there. The database is not reachable, the service is just returning whatever answer, or the model start hallucinating and so on. So because of that, we need, when we have this integration point, we need to add them or decorate them with other enterprise features, like observability. We want to know how many times we call them, the time it takes, while having the metrics, the tracing, auditing, pricing, so all your tokens and things like that will be there. Things can fail. So we need fault tolerance, so we need retry, we need circuit breaker, we need all these well-known resilience patterns, all that integrated for you. And obviously we need security. It's not on the slide, but as you can imagine, in 2025, if you ignore security, something bad is going to happen very quickly. So you need security enforcement at that level, like making sure that the model you interact with is allowed, and you don't give any extra information inside the prompt, you don't give information you don't want to send to the model, and things like this. So, and basically AI service has been designed to be, at least the Quarkus one, to be all this together, to be this integration point and represent that integration point. Obviously, it uses a chart model and memory, but it's also decorated with observability, with auditing, with guardrails and things like this. So, and security and so on. So, inside your interface, you can use plenty of annotations to configure all this. You want a retry, at retry. You want a circuit breaker, at circuit breaker. You want to allow only the roles systems, role allowed system, or whatever is the name of your role and things like that. That's it. So everything is simple for you. If you go with the other more flexible model, chat model, or even LangChain4j chat model, you will have to do that work every single time yourself. It's doable. Well, we did it, so we believe it's doable. But
Definitely.
You will repeat that over and over again. So again, question of choice. Do you want flexibility and maybe more code, or do you want something more opinionated with everything packaged for you? So, and one thing that is also important is how we manage memory for you. Depending on the scope of your AI service, we will manage the memory differently. And instead of explaining that slide, I'm going to go to the demo. So it's not my machine, and it's even using Linux, so I'm completely lost. Oh, no, I want this. Oh.
No. You are killing the wrong server. Okay.
I need my own server on 8080.
Okay, which one do you want to run? It's the services, right?
No, the next one.
The next one?
Yeah, and it's scope. So 3.2.
3.
No,
Two.
the one before that, 3.2.
Yeah.
It doesn't have a public static void main, so you can't.
Okay.
I don't believe. Or I can create one.
Okay. So we need to run it. May I help you?
Let me try something. No?
It's just
Quarkus.
Quarkus,
Quarkus dot run. Yeah. And do I need a Quarkus main? Let's see.
I think you also have to add the class itself.
Yeah, you need to pass the name of the class.
Yeah. Well, seems to have worked actually. Oh, surprising. I don't know if it's a feature or a bug. Voila.
Nice.
Seems to work. Yeah, probably a bug. Anyway, so what I wanted to show you here is, so first this is a dev UI. If you discover Quarkus, it's your toolbox. You have all the tools you want directly integrated here. And for this demo, I'm just going to use the Swagger UI, because as soon as you have Open API, you have the Swagger UI built in here. And the first one is my AI service is request scoped. So I create an instance of the AI service when the request is in, and when the request is flushed and sent back to the users, it's deleted. So if I go there and I do try it out, and I say my name is Clement, execute. So you will create the instance of AI services with the memory and so on, and then the request is gone. Now you say what is my name? Well, I don't know where is the question mark, so let's see if it works. Because we even don't have the same layout. So it said, no, sorry, I don't have that information. And that's right, because the memory associated to my first request, knowing my name, is now gone. So in that case, there is no eviction and so on. It's the scope of the bin will serve as eviction strategy. So obviously, that's a bit of hard to create a conversation with such kind of things. Like it's a bit annoying. So now I'm going to use something which is application scope. So you create the AI service, but once the instance is created, it will stay there till the end of my application. So if I say my name is Clement, and I do execute, then it say, hello, nice to meet you, okay, assist you. But now if I say, what's my name? Still no question mark. Ah, over there. I was like, Italian don't use question mark, maybe. And now it remember me. The problem with that is that, okay, great, it remember me for the lifetime of the application. So if now Georgios come in and say, my name is Georgios, it's a little bit weird. And the funny thing, because we know that Georgios is a hacker, he will be able to extract all the information I gave to the model about me and use that. So we need to be very careful. So here there is no memory isolation. There is a single memory for the lifetime of the application. So be very careful with that. To implement this, I had actually to tweak something because normally it's not possible. Oops. What is your ID?
Yeah, that one.
That one? Oh,
no,
yeah.
no,
that one.
Yeah.
So the long memory assistant has actually a memory ID, which should be basically your session ID or user ID. So to implement that demo, I think something that you should not do is passing the same memory ID every single time. And obviously, if we do a multi-users application, I will have a memory ID, Georgios will have a memory ID, and our memory are not going to be
won't overlap.
Yeah, won't overlap. So the next one, oops, damn it, so many tabs. I need to go back here because normally when we, no? Okay, even the clicks are slightly different, that's weird. Yeah, okay. The next one is using a WebSocket, because when you use ChatGPT or something like that, it's basically a WebSocket. So you are starting a session, and then you can stream messages back and forth from the WebSocket. And we implement the same kind of behavior here. You can go to WebSocket next, server endpoint, connect to this one. I want to send something, and I say, my name is, or let's change a little bit. My name is Mario. That's not true. Okay. Nice to meet you, and if I say, what is my name, then it say, oh, your name is Mario. Because in that case, the memory is isolated by the WebSocket session. So if I disconnect and reconnect and say, what is my name,
can do it.
Yeah. At the end, I will be fluent on this keyboard. Well, it will tell me, no, I don't have that information. Because I close the WebSocket, and because I close the WebSocket, the memory associated to that WebSocket, to that session, has been, well, erased. So that's how you can do memory isolation very quickly with a CDI-based scope. Obviously, you can also implement your own behavior as you want. You can persist that memory in any kind of things like database or Redis or whatever. But you can also do it like this. No. And now let's go back to the slide. Yeah, here. Okay. Slideshow. All right. So we have seen an example like this, but you can template your prompt like this. So the parameters from your AI services can be passed or filled directly inside your prompt. Depending if you use LangChain4j or Quarkus, we use different templating models because obviously we didn't agree. So LangChain4j use two braces, we use only one.
Well, it's actually an artifact of how it was implemented.
Yeah.
So in LangChain, you use like J mustache or whatever.
Yeah, and we use Qt.
We use Qt.
And we are more lazy, so it's one keystroke instead of two. So I think that is the real reasons why we do that. You can also navigate inside your object, so you see question.players and things like that. So you can send such kind of things. There is plenty of other capabilities around that in terms of observability and so on. We will see some screenshot of what you get in terms of observability. We are not going to run observability demos here because, yeah, first it's a big Docker container to get your all observability stacks and, yeah, the result, and it's not really visible. However, if you want to implement observability, that's very, very simple. You just add the observability stack in Quarkus. Quarkus observability and how do you want to publish your metrics, like Prometheus or whatever. And that's it. As soon as you do that, you get this. So you will get all your span. So typically you see here that I've called GPT-4o and so on. So it's spent here 2 seconds and things like that. For every span, you can also get the number of tokens that have been sent. And if you implement a pricing simulator?
Strategy. I don't know.
Yeah, pricing strategy where you mimic the pricing of your model provider. You can also have an estimation of the cost of every single request, which can be useful. You can also have this view, but yeah, it's not sure it's actually very useful, but yeah. Anyway, as I said, you can also have fault tolerance, so you can use any of these applications, retry, timeout, fallback, circuit breaker, rate limits, and things like that. So you just add that. Dependencies, you use the annotation you want on your AI service method, boom, you're done. And the next level is function calling. And I think it's, do you want me to do the side? Or yeah, do the side. Oh, you do? Yeah, go ahead.
Okay. Yeah, so yes, as Clement said, it's quite typical that you want to provide some more features to your agent, and especially at least at the beginning, these LLM things are well known to be not so good to do some kind of stuff like math, for instance. So they really often hallucinated it even with simple math operations. So I believe they started using function calling for this reason. They wanted a reliable way to do math operations. So you do math operation, not letting the LLM to do token concatenation or hallucination, but you want to do this in an algorithmic way. And of course, you want to do the biggest part of your task, of your application, probably in an algorithmic way, in a fixed way, in a deterministic way. So this is why you need to do function call. You want to provide your LLM, your AI service with this tool, doing stuff in a controlled way again, and the agent is supposed to be smart enough to understand when it needs to call a tool instead of doing stuff on its own.
And one thing to say about that is that if you use something like Claude, CLI, and things like that, how they interact with your IDE, with your code, and things like that, is using function calling. So it has this magic thing around it, like, oh yes, that's great, I can integrate everything. At some point, we even have models that were taking screenshots of your screen and was reasoning about that. But yeah, so that's how it works.
Okay, and the way how an AI service actually call a function, it's not that straightforward. I mean, I remember I was a bit surprised the first time I learned how this thing works. Now, of course, it makes sense. But what happens basically is that when you send the prompt to the LLM, automatically LangChain4j or the Quarkus integration also recognize the number of tools that you are providing to the LLM. And then it creates a JSON that not only contains the prompt, but also contains the list of tools that are available to that LLM together with the arguments that they need to be invoked. So the LLM ingests all this JSON and decides if it can reply directly or if it needs to call a tool. If it needs to call a tool, it returns with a request for a tool invocation, and then this tool invocation happens inside the LangChain4j or the Quarkus extension again, and then the result of this tool invocation is sent back again to the LLM, and then the LLM does this, let's say, loop again. So maybe it may want to decide to use another tool again, or it may finally be able to provide a response on its own.
So typically on this slide, everything on the right happens in the model. So not a lot of things. Everything on the left happens inside your AI-infused application. So you are still in control.
Yeah, so that's the key here. The key here is to understand that you are telling the model what to invoke, okay? Well, sorry, you're telling the model like what you have available. The model comes back and says, okay, go ahead and invoke like whatever you should based on the specific request. But your application is the one that is actually invoking the tool, right? Or in an MCP world, I should say, it's coordinating the invocation of the tool, right? The model serving part never actually runs any of the function calls you're specifying. You have to run those. You have to tell the model, okay, here's the result, and then the model will say, okay, fine, I'm done, or execute another tool, or you can even execute like multiple tools in parallel, right? So yeah, I think we should probably see this in action, right? We have a demo about this because like all this is very vague, right? Like we're sending JSON, we're getting back JSON, and it makes a lot more sense when you actually see in practice what this JSON looks like, what we're sending, what's coming back. So that's the point of this demo here. Let's hope everything will go according to plan. So it's function calling.
So as you can see, there is a lot more demos
that
you can run at home. We have to go pretty fast because there is tons of content.
Maybe we should like give the URL of where people can find these.
It will be at the end. So you will have to stay till the last slide.
Yes. One more reason to stay.
That's a trap.
Exactly.
Marketing. Oh yeah, that's not a trap. That's marketing. Sorry.
So here, we're using an AI service. Oh, are we using the right one? Function calling. Yes.
Yeah. With new calculator.
Okay. Yeah. So we're using the Builder API.
So pure LangChain4j.
Okay. Excellent. So let's go and see like what this looks like, right? So with pure LangChain4j, we are setting up an AI service using the Builder. Passing like what the chat model is, chat memory, but the important thing is this calculator, right? So this is basically just a Java class where we have 3 methods annotated with @tool, right? And the very important part here is to see like what description we give to the tool. Like each tool says like calculates the length of a string, calculates sum, whatever, square root, all that stuff. This is super important because this is what actually goes to the model, so the model can understand and match based on what the input is from the user, if a certain tool should be invoked or not. And also, like if you have multiple parameters, like in cases of math, like it's very easy to understand like what each parameter is. But if you have like other parameters, you would have to annotate them as well and provide an accurate description. And we'll see that later on.
One thing important is that this is based on this description that the model knows when and how to call your tools. So if you call your function foo and your parameter bar and bars, it's not going to work. So you would have to use meaningful method name, parameter names, and so on, and extend them with description so to make sure that it can narrow the right call.
Okay, cool. So this one just shows, actually this just shows like what we send, what the result is. But if we go to the next demo, which we'll see, which is the Quarkus one, then we will be able to actually make it show the JSON output, right? So let's go to resources here in the second one. Okay, go to application. Let's make sure that responses. Okay, so like let's take out the
remove the test.
Thing, so we can actually see what's going on. Cool. No. Just leave those. Just leave those.
You don't want to use them.
No, we don't use. Yeah. So this is cool. Okay, cool.
Yes.
So what these 2 properties do is just enable the logging of JSON input and output, right? So let's go ahead and run this. This is pretty much the same example, but we'll look through it. What I'm looking for here, excellent. That's what we want to see. You're terminating the previous one. Good idea.
Okay.
Cool. Okay, so let's start from the top, and well, we're not going to go through this whole thing, right? Let's just try and give a basic overview. So, because this function calling is like super important to understand, what the first level of let's say agentic behavior looks like. It's not an agent, but it's a first level of how you go. So here, okay, when we're sending the prompt, right, we're also sending an extra section in the JSON that describes all the tools that we are telling the model that the tools that are available to our application. And Quarkus, obviously, Quarkus LangChain4j builds all this up automatically, so you don't have to do it. But this describes the tools in all the detail that the model needs, and obviously like OpenAI has their specific format, like Anthropic has theirs, but they're very similar.
Well,
So
OpenAI use OpenAPI for that description, which makes a lot of sense.
okay, yeah. Okay, so if we move further down now, okay, yeah. So these are the other tools, and now here's the response, right? Mm-hmm. And okay, cool. So here we go. If you could go a little up for a second. Just a little, okay, cool. And now the model comes back and says, you know what? Now what you need to do is you need to call a function that's named string length, and it actually gives us what the arguments are, right? Because like our initial prompt was like calculate, like, I don't know, the sum of all the letters in the hello world or something like that. So the first thing it had to do is like, find the length of a string, which the model doesn't know how to do on its own, and we provided a tool. So it tells us that, you know what, this is what you need to do. Then after we do that, we execute that on our own, and we'll send the response back, right? So if we move further down, if we move here, now we say, okay, you know what? Here is the result. The string length that you were looking for, that you model told me, is world, right? And let's keep in mind what Clement said earlier. That's super important. The model itself has no idea of what like this whole conversation is. So we are sending the entire conversation every time. So we're sending like, what's the prompt here? What tools that we had? What the model told us to do? And now we're saying, okay, here's the response to the model. And if we kept going through the whole thing, which we're not going to go through now because there are a lot of function calls in this example, we would see for each call, we would see the same thing. Model telling us what to do, we send the response, model comes back, says, okay, cool, tool called, blah, 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 until we reach the final result, which would be, I think, at the end, and it would say, like the result that you were looking for is, I don't know, 42 or whatever.
And they are tokens, and you are paying for them. Just remember that all the exchange that Georgios is saying is token going forward and backward, so you are paying for
we have the number of tokens. For this very simple example, it's already 225 tokens.
So yeah, that will make your model providers very, very happy. It'll probably make your finance department less happy.
And one thing also, as soon as you do function calling, context summarization or compression of context start to be slightly more complicated because you must not compress in the middle of the function call. Otherwise, it would be lost. So yeah, you need to take that into account too.
Excellent. So yeah, I think we covered function calling, right?
Okay.
Yeah, so let's move on because this is just the Quarkus version, which, as you expect, it's like a lot. It's simpler to define because everything's declarative. You use the Register AI service where you could define the tools on the Register AI service, which that makes sense if you have multiple methods inside. But
using all the same tools?
Yes. Or you could use this at toolbox. And now, of one thing that one choice we made that sometimes users don't fully appreciate is that we don't include all the tools in your class path by default, right? You could have like 100 tools, but we don't include any of them unless you tell us what to do. The reason is because some of these tools could be like very security sensitive, so we want you to opt in to whatever tools you need for each example.
And one thing to remember is that models, again, are teenagers. You give them a lot of tools, even if it's not really related to the task, They want to play. So you need to reduce the number of tools to really what is required to achieve the task, and that's it. Also, more tools you give, some models will start hallucinate and won't be able to call the right tools and things like that. If tools have close name or close descriptions, things can really quickly go south. So be very careful with that.
That's a very good point. Yeah.
Yeah, that's why we want you to explicitly list them. Well, there is a tools provider that you can use if you really want to do that. But
yeah, there's a lower level way.
Yeah. This last thing is something that I really experienced when we started integrating the MCP, meaning that you give what we did at the beginning is that you just give an MCP server, a whole MCP server to your AI service, and these MCP servers can come with tens of different tools, and not only the JSON is very big. At some point, Stefan opened an issue because he cannot use the tool, the MCP server, because the token window was really too big. But except for this, the problem is that hallucination, because if your task, if your model just needs a couple of tools and you are giving 50 of them to the tools, it's very likely that it will start requesting the wrong tool or a non-existing tool at all. This is also something that happened. Yes.
And look, depends also on which model you are using, because there is models that are better on calling tools. If you see in Olama tools, doesn't mean that it means that it is able to call tools, but not necessarily very well. So depends on which model you are selecting.
Yeah.
Great. Okay, so I think. This is a bigger example. I'm not sure.
No, we don't run it, but that gives you some ideas. Like you can actually give access to a database, like just using add tools on a Panache repository in Quarkus.
Yeah. So the idea is that it ties in with all the rest of the Quarkus ecosystem.
Exactly. Right? So we have also an example with the REST client, the next one. So you can actually call a remote client directly using add tools on a REST client. So that, you can do that. You can also go a little bit further and say, hey, why another AI service can't be used as a tool to a first AI service? And that was actually our first step in the whole agentic world. And we were thinking, when I wrote that demo, something very close to that. I was like, hey,
we're done.
We're done.
We're all set up.
4 letters, and I'm done. Everything. If you start doing this, believe me, it won't work. The thing is completely out of control.
It'll work for demos, but
exactly. If you run this, it will work. But in a real serial things, don't do that. And that's why we have the rest of this presentation that will tell you why we are not doing this and why we have something. Well, we need to keep a little bit of control on that. Obviously, we didn't mention, but all the function calls are also traced, so you can see exactly what is called at what time. Again, tokens, pricing, everything will be integrated.
Yeah, so you see on the left like what the span is for, and then like timing for each thing. And if you click on each one, then I think the next slide probably shows you. Yeah, like you have. There's an incubating, let's say, specification about like Gen AI metrics.
Yeah, Open Inference, I think it's named.
I don't remember what the name is, but yeah, we implement it now. I'm sure it'll change. We'll keep on updating it. So
I knew that I should not do that on a Linux machine. So I cannot use my pointer, but basically you see I'm not sure you see it, but you see the number of tokens at the end and the number of prompt tokens. So everything is inside your
which is super important, like for when you're like actually doing stuff in production, right? You want to know what happened, why it happened.
Okay. Guardrails. Who is doing Guardrails?
You can do it, yes.
We have no idea what's going on, so don't worry. We are LLMs in actions.
Four people, totally remote, trying to coordinate a 3-hour presentation.
Okay. So guardrails are another key function for LLM. Also security and are also a good tool to avoid prompt injection, because like we have there is some similarities between an LLM and a database. In a database, you can have a SQL injection, and with an LLM, you can have a malicious prompt that could try to do nasty stuff with your LLM-based service. So for this thing, we have an input guardrails, meaning that it is something that validates the prompt before hitting the LLM, before propagating that prompt to the LLM. So you can say, okay, everything is fine, of course, move it forward, or you can simply rephrase it a bit. You can simply modify it a bit before moving forward. But in my experience, this thing probably is almost never a good idea because you are confusing the user in this case. I mean, he asked something, you are propagating something slightly different to the LLM. So it is possible.
Except for anonymization, where it makes a lot of sense.
Okay, yes.
But except that use case, yeah.
Yes, okay, true. So in essence, you can control the kind of input that is sent to the LLM. And equally important is also on the other side. What you want to have control on what the LLM is replying to you. You want to avoid, I don't know, bad mounting a concurrent. So
mentioning a competitor, detecting hallucination,
yes,
because you can actually detect hallucination in a output guardrail by verifying that the response is close to the extended data you added to the request. So there are ways to do that. Yeah.
There are ways. Something that you can do is using inside the output guardrails a second LLM that can validate what the first one did, for instance.
Typically, this is used to know, depending on the context size, in which case you are not enough context, right context, or too much context. So this second LLMs will be able to tell you a level of trust.
There's a pattern, I think it's called LLM as a judge. Yes, that through which you do this stuff. Okay, and even in this case, the LangChain4j, originally this thing was developed in the Quarkus extension. Then, of course, we figured out it was a very general and useful thing. So what we did is moving that implementation from the Quarkus extension to vanilla LangChain4j. So if you are using LangChain4j now, you also have access to this guardrail feature.
Except for stream responses.
Except for stream responses, yes.
You need a reactive model for that.
Right.
Plain LangChain4j doesn't have one yet.
Yes, maybe we can see. Okay, so sorry, these are the possibility that you have in the output guardrail. So you can say, okay, everything is fine. Please go forward, and the success can also be success with a result, meaning that you don't want to propagate exactly what the LLM replies, but you want to provide your own reply to it, or you can say, no, this is a fatal error, don't propagate any result, and maybe throw an exception, or you can try your luck and simply retry the same prompt.
It works on teenagers. You ask the same question 10 times, the answer changed, and sometimes improved.
Yes, sometimes this works.
Sometimes the opposite.
Or even better, you can reprompt, meaning that you cannot simply retry with exactly the same prompt, but you can add more context to your prompt before retrying it. So let's try.
Yeah, and this reprompt strategy is actually very interesting in the sense that it's a resilience pattern that is only available on AI. Like, you can't really reprompt on a regular web service. That doesn't make any sense. But here you can say, here is my error. How can I improve it so it actually works this time. So you have that possibility.
Okay.
So start with the first one.
So, yep. So let's
show maybe the
sure.
Yeah. Otherwise.
So let's see how my service is configured. I have this usual assistant that takes a user message and replies something. But in addition, I have two guardrails in both directions. I have an input guardrails that propagates the message to the LLM only if the message is completely in uppercase, otherwise it blocks it. And so
if it blocks, it doesn't call the LLM at all. So imagine that it's bad wording or something like that. No, I'm not going to call it.
Okay. And then I have a second guardrail, this time on the output. So it happens on the response of the LLM, so I can read the response of the LLM and filter it in this case if I also want the message to be completely in uppercase. So what I say is that, okay, if it's in uppercase, it's fine for me, just propagate it. Otherwise, try this reprompt strategy. Try to reprompt again the LLM with a slightly different prompt, convincing him that you want the output in uppercase. So we can try this thing in a few situations. For instance, here I'm sending this message to the assistant. Now you should probably already have understood what's going to happen, meaning that my message is not supposed to pass the input guardrail because the input guardrail is blocking all messages that are not completely in uppercase. So I'm just getting this exception telling me that the guardrail fail with this message. The input must be in uppercase, otherwise it cannot hit the LLM at all. The input guardrail will block it. So let's give this a second try with a proper message saying hello world. Let me stop all of this. Okay. Okay, so what's happening now? Okay, this was quick, but basically the LLM replied to me in this way, and then sorry, one step back. Now the input is all in uppercase, so it's valid. So the input guardrails is not complaining anymore, and is propagating the message as it is to the LLM. The LLM is replying to me with this hello world, but now the output guardrails kicks in and checks that I want to also the outcome of the LLM to be in uppercase. Otherwise, I will try with this reprompt. So the LLM is telling me hello world in normal case, in lowercase. So what happens is that you should see somewhere this reprompt here. Nope, sorry. Copy. Where is it?
The second message now. Please provide your answer. If you look for please, that should be fine.
Ah, this one. Sorry. Yes. So this is the message that is sent actually to
the user. Well.
To the user, and this is for the LLM. Okay.
I always say please to an LLM. We never know.
Okay. So yeah. So the LLM is telling me hello world in normal case, and I'm telling to this thing, please provide the output in uppercase, and then you have a second invocation of the LLM, and this time is telling me hello world in uppercase, so it's also passing the control of the output guardrails and telling me hello world in uppercase. Okay, and there is a third flavor of this thing, which is probably more interesting. Maybe Clement, you want to clarify?
Yeah, I can cover that one. So, no, I'm going to ask the LLMs the same question. Say hello world, all in lowercase. Okay, what will happen?
So we are trying to confuse the LLM now.
Yeah. Well, that's what we're doing all day long anyway. So it returns hello world in uppercase. So why? Because we send that prompt, the prompt passes the input validation. It's all uppercase. So the model will say, will reply to hello world in lowercase following the prompt. But then we have the output guardrails that will say, no. Do that in uppercase. So in your memory, you now have, say it in lowercase, hello world in uppercase, in lowercase, and a new message, a reprompt that say, do it in uppercase. And we send that again to the model, and the last message wins. So in that case, it will return hello world in uppercase. So that means that Guardrail can actually change your prompt or change the answer you expect. So that also allows kind of a small protection against malicious users, because you can make sure that the answer you get is it's not leaking.
In this case, it works because there's like no system message that said do it in.
Yes, if we would have a system message, and the system message would have win. Yeah. So, but yeah, system message are higher priority.
And anyway, the output guardrails wins in all cases. I mean, even if we do a prompt, you are not able to convince the LLM to do this in uppercase. Anyway, the LLM at that point will reply in lowercase, but it will hit the output guardrails again, and the output guardrails will block it anyway. So there is no way to escape this. Okay.
Famous last words.
Okay, so these are...
So typically, that's exactly what happened on a reprompt. On a failure, we basically create a new user message that we add at the end of the memory. That's what explains the last behavior, because we add it at the end of the memory and we send that back. Again, more reprompt, more messages, bigger memory, bigger price.
I don't know what's next.
Okay.
So that we are ready. So
this? MCP, Stefano.
Okay, so MCP. Before starting on MCP, a quick question: who is using MCP?
Oh, okay.
Not so many. Nice. And who is writing MCP? Different people. Nice. Okay, so MCP. Let's try to demystify a bit what MCP is. But basically is the client-server version of the tool calling. So the protocol is a protocol. P stands for protocol, and MC stands for model context protocol. So return a bit on the name, and is a protocol to enrich your model context. So basically to inject something in your context. And what is injecting? The tools first, and probably is the most used at the moment feature, injecting the tools, but you can also inject resources, which are data, which are content, like URL, and so on, but also prompts. So basically, what are we doing? Exactly what we are doing with the tool calling that we explained before, for the tools at least, but in a standard way. So we are defining a protocol to define a server on the right side and the client on the left side. The client is typically the chatbot or the model somehow, and the server could be anything, something that access to data, access to another model eventually, or to access to prompts. So those protocols define those as client and server, and so as any protocol need a transport layer. The transport layer that is available in the standard are basically JSON RPC. The protocol is based on JSON RPC 2.0, but the transport could be standard IO, that is the most used currently for MCP, at least in the agents that are like coding agent or local agent that you are using. And then remote one. The server, the SSE one is deprecated now in favor of streamable HTTP. The reason of that is basically that SSE has some problem, especially with network problem like firewall and things like that could kill the connection. While streamable HTTP, which is the same used by OpenAI on their API, is much more stable. This is the very first step to move to an LLM and AI service, AI-infused application to agent. A single agent, well, the most accepted definition, if there is any most accepted definition of agent, is an application that has tools and resources and can iterate over a problem until it gets solved. The most easy example is coding agent. Coding agent is using tools to read the context that your application has, call tools, as a prompt predefined and normally is MCP or MCP-like. Claude Code and Gemini CLI, the most famous one, are using both MCP for that, and try to find a solution. But of course, you can move the same concept to the agent and to the remote agent in Quarkus. So we can say that is the protocol like SOAP was for web service.
Everybody loves SOAP.
Yeah, everybody loves SOAP, but everybody is loving MCP now, so is almost the same.
The same level of love-hate, yes.
Yeah, the same level, more or less. So the idea is to have those data store and MCP can use data, can use any tools and also any prompts, and it comes to problems here sometimes because security in MCP could be a very big issue. Is not well. We can return here later. Let's go on for the security part. Security is not very well defined at the moment, to say the less, and so there is many surfaces that you can attack through MCP because. Return to the name, model context protocol. So you are injecting something in your model context. The problem is that you are using most likely external MCP that you don't control sometimes because there is many vendors that are providing their server, but you are basically, the best definition I read is you are using prompts and the data that someone else wrote. So what can go wrong? Almost everything. Because if you have a prompt injection, you can do something very bad. And also, it's not just prompt injection. There is other levels like tools injection. So a tool that is malicious by itself, that doesn't appear to be malicious, but prompt your model to do malicious things. And there is also supply chain problems, for example, because maybe the first version is very good and the last one is very bad, and you are not getting that. Okay. Yeah, that's what I more or less mentioned already. And yeah, how is provided on MCP level? I don't know if we have an example.
Yeah,
I think we do. Yeah. So this, what you see here, is the client, right? It's the client side.
Go on.
No, go ahead. So I should note that in Quarkus we have in Quarkus LangChain4j there's an implementation of the MCP client side, but in Quarkus we also have a project called the Quarkus MCP server where you can write your own MCP server, and we have both here, right? So here is we're gonna define a MCP server which exposes 3 different tools, right? And they're all weather related. So this is how you write it. It's so simple. It's mind blowing, right? You just annotate with tool, and then you can use whatever other Quarkus constructs you want, like the REST client here, right? And that's it. As a developer who wants to write an MCP server, this is all you have to do. This takes care of all the protocol layer stuff, the transports, all the advanced MCP server features like elicitation, cancellation, all that stuff. Obviously, here you don't see that, but I'm just what I just wanted to say is like I believe this is the simplest way to write an MCP server, right? And you can, of course, introduce security with the standard security annotations. But this is just the server part, right? Server part exposes a few tools, and if you go to the client side, you have to go actually to the resources first. Well, yeah, first we annotate with MCP Toolbox. MCP Toolbox means that for this AI service, go ahead and use all MCP clients you have configured. And we have one MCP client configured here, which is the weather client, which is using the HTTP transport, and it's using the URL that we have started. Well, the URL of the MCP server we have already started, right?
So it might be confusing, but it's named HTTP, but it's streamable HTTP, and right now we are the only Java implementation implementing HTTP.
Yeah, so that's the other thing I wanted to point out, that our MCP server, I don't know if you've actually seen that we implement the new things that come out of the spec really, really quickly. Like, I'm not even sure, like, cancellation is supported anybody else, like elicitation.
Elicitation, yeah.
But yeah, it's very, very good. And, like, we have all transports at this point. And we might like WebSocket in the future.
We are working with other teams to actually implement new transport because some make a lot of sense. Like WebSocket will simplify a lot of the things.
But the whole thing is like, as a developer, you don't have to care, right? You just use Quarkus MCP server, annotate with .tool, and you're done, right?
Also, into your MCP toolbox, you can also mention or list exactly the tools you want. So here, in that case, if you could refer it to as weather. Mm-hmm. And then if you have many MCP tools, then you can actually limit the reachability of your MCP tools. Again, as I said, generally a better approach. And we use a different annotation because we want you to be aware that this is going on the network. So this is not staying here, so security, observability, and things like that need to be slightly different.
Okay, so let's see this thing in action.
So you have to open up localhost 8080, so yes, get the chat.
So here you can experience my fantastic skills
in JavaScript.
Sure.
You love JavaScript, don't you?
Yeah.
Nope.
Oh, that's a queue they have. No CDI.
Is something else running, perhaps?
Yeah, probably, yes. Yes, I have tons of stuff running at this point. So, let me kill all this stuff. So this is on.
And Quarkus tells you how you can find like what else was running, right? It gives you like a.
Well, we have also a Quarkus skill
Quarkus kill, command.
Which will kill all the Quarkus instances running. So clean slate.
So this is not running at all.
Of course, for production.
Again.
No, you still have one running on 8080.
Somebody's running 8080.
Okay, so let's do.
No, it tells you the command. See, it says use. Yeah, that.
This one.
Yeah. Just run it. And let's see.
No, not with the or. That doesn't. Just the first part.
Yeah, there are two different commands. You're right.
This one.
Yeah. No, just stop at the or. SS on up grep. On up. Yeah, grep.
Grep.
Yeah, grep 8080. Otherwise, we
see everything.
We want to see Quarkus kill.
I don't know if we have it on the.
There is
if Mario has the CLI
lots of
here.
stuff going on here.
Are you sure you don't have one? The Guardrail application seems to be still running.
See, there's a PID. It's like 301.231. Right?
Yeah. So you can kill this one.
Kill
what? Which one?
301.231. 301.231. No space.
No, yep. And we are very lucky.
Like it was not the kernel.
Okay.
But you don't find it.
Maybe it came down.
Let's give this.
Maybe it came down already.
Run.
Kill 1. -9.
Okay.
Okay, now it's working. Okay.
Hop. Finally should be working.
Yes.
Look at that UI.
Yeah.
You've never seen a UI this good.
Yeah. Okay, so
you're front-end developers, that's for sure.
Yeah, I am. I have a future like. Okay.
Yeah.
So this thing is telling me I'm a weather service. Let me try to ask what will be the weather tomorrow in
Well, that's easy. Cloudy, rainy, cold.
So while this thing is running, let me explain what's going on here, of course. So as Georgios says, we have this service that is defined here on the client. So the client knows that he has to use this weather service running at this URL. And with this annotation, I'm actually providing to my AI service all the MCP server that have been configured, only one in this case. But of course, sometimes, as I said before, this could be a little bit overwhelming for the AI service. So you may want to have more control and decide which of these tools you want to actually provide to the AI service, and you have some properties of this annotation to define this, but I don't need this now. What this thing is doing is calling this tool, and what this tool does is, first of all, I need to geocoding my town. So I found the geolocation, latitude and longitude of my place, and then I hit the weather forecast to have the forecast for that latitude and longitude. And at this point, I should have an answer, which is not bad for Belgium.
Basically what I said.
Yes. Well, it's not that bad for Belgian standard, as for what I can understand, but yes.
The thing is, it calls the MCP server multiple times because it calls multiple tools. So you have one server, multiple tools, and here you ask question and say, okay, first, what is the geolocalization of Antwerpen? So you look at that and get the response, and then the LLM say, okay, now I can call these second tools, and every single time, the AI.
So I would highly suggest running this locally after we show you at the end of the talk where you can find all this stuff. But when you run it locally, you actually see and you get the magic demystified, right? It looks very magical right now. When you actually see the output and go through it, it all makes perfect sense.
So this is already the second part of the interaction where I found where it found the latitude and longitude of Antwerp and is calling the weather service by passing again the latitude and longitude that has been provided by the first MCP tool invocation.
And one thing to add is that the model has no idea that these tools are served using MCP. So this is all it done. The model doesn't know if it's local, remote, whatever. The model just say, oh, I have that tools, let's invoke it. And then you have Quarkus that will just do the work to invoke the tool.
Yeah, there is a trade-off to decide how many tools to put in an MCP server or provide multiple MCP server, because the server itself has a description, so it's like giving the LLM a sort of tree to navigate, to find the right tool to call. So too many tools in a single MCP server could confuse more the LLM than having multiple MCP server with a few tools.
But you save in terms of connection, because you will have one per server. So it's
there is always a trade-off.
Yeah, it's a
play
trade-off.
with that.
Okay.
Right. Yeah. I think that we did. Yeah. Okay. So now it's a break. We will meet.
11:20.
30.
15 minutes.
15 minutes. Yeah. So. After the break, so we have done all the foundation. So now you have all the building blocks to actually build truly agentic systems, and we are going to see how just after the break. So come back if you really want to see the meat of it.
We are really going to put all this thing together and create agentic system now.
15 minutes.
Yeah, 15 minutes.
Thanks.
All right, let's restart. So as I said before the break, until now, we have seen the foundation, all the building blocks we are now going to assemble all together to truly create agentic framework, an agentic application, and agentic systems. And the first thing we are going to see is the workflow APIs that we have been adding like over the past few months that Mario has implemented. And basically, the idea behind the workflow API is to assemble your AI services and your agent while you are still in control. So it will be like doing it with code, but with higher level abstraction. And when we started doing that, we were thinking, well, that would be super easy. And we realized that we are missing a lot of construct underneath to actually build that on the right thing, and that's what we are going to discuss now. So this is based on the work from, a paper from Anthropic from last year, I think, something like that.
Yeah, November last year, yes, it was, yes.
Or they identified 4 different patterns to assemble your AI services all together. So sequence, routing, parallel, loop, and things like that. So we took them. First thing we did is implementing that by code. We're not going to show that in this deep dive, but we have other session where we are going to show you how this can work. But we looked at that and say, well, that's a lot of boilerplate. There are a lot, yes, you are a lot of control, but it's a bit, really, you need to do everything yourself. So how can we actually improve that, improve the experience, improve the composition of your AI services and of your agent? And that's what Mario is going to present now, because that is work, totally.
Okay, so it all starts with a single agent. Now the challenge is to put them together. I have 3 different agents here, and but I want to, of course, coordinate them in order to provide a service that make use of all of them. So let's start with these 3 things one by one. The first one is a creative writer. It takes a generic topic and it generates a story fitting that topic, about that topic. Then I have a second service, LLM service, which is an audience editor that takes in input the story generated from the first and takes a second input, which is the intended audience, and it adjusts the original story for that audience. And then I have a third editor, a third service, which is the second editor, that does a similar thing, takes the story produced by the audience editor and takes in input a style and does a further adjustment of the story for this given style. Okay, so what I'm saying is that I have this, at this point, these three independent agents. But in reality, what I want to do is to provide a service that takes in input. So this is what I want my user to see. It's a service that takes in input the topic, the audience, and the style, and it produces a story. This is the service that I want to expose to my user. It doesn't need to know that internally it uses these three agents. So what I'm saying is that I want an agent that exposes this interface. That's all. I want an agent that takes those three arguments and generates the story. And okay, here you can see a usage example. I want to generate a story about dragons and wizards for your young adults, and of course the style is fantasy. Okay, so let's see how to do this. First of all, you can instantiate these three agents in a very similar way how to do with the AI services with the programmatic API in LangChain4j. For agent, we have this single entry point, which is that agentic service class, and you have tons of factory method to create this agent. So you are provided with a builder, and then you provide the service, in this case, with a model. The first difference of agent compared to AI services is that I'm providing an output name. I'm saying that the name of the output provided by this first agent is the story. Okay, and then I build the agent. I mean, at this point, I have my still three independent agents. And then, of course, I want to put them together. So this is the first kind of pattern that we will see, which is a simple sequence. It's also what is called in that Anthropic paper a prompt chaining. I'm chaining the prompt. I'm using the output of one LLM as a prompt for the second, and the output of the second as a prompt for the third. So I'm creating a sequence of these three agents and saying again that the output is a story, okay? So what happens in reality is that I invoke my API, my service, the one taking the topic, the audience, and the style, and then all these things goes to a common area, shared area. What the missing bit of this agentic architecture compared with the fact that you have the three independent agents is that you, at some point, you need this thing to talk to each other. And to do this, we have this shared area, meaning that at this point, the topic, the audience, and the style that are taken from the user call are put in this shared state, and then the three agent write and overwrite the story, and this is still something that goes in the shared state. So the audience editor, for instance, take the topic from the state, take the audience from the state, and produce the story. And then the style editor will overwrite it again. And then you will have the last bit that will simply output the story. Okay, so this shared state, we call it agentic scope. In reality,
are you sure?
In reality, originally for UFO, for people like Guillermo who follow the evolution of this, it was called the Cognisphere. Yeah. It's again, this is another teaser for our talk tomorrow. you want to know, really, you want to know what the cognosphere is. So come to the talk tomorrow and you will figure out how we get to this agentic scope and what was the cognosphere at the origin.
But anyway, yes, we are bad at naming things.
Yes,
yes. Which you can also see in our Thursday talk about mistakes we made during development of Quarkus. Naming is a pretty big one.
Okay, so as I said, in this agentic scope, you really have the shared state, the common state of your whole agentic system. So not only you have the shared variables, but what this agentic scope does for you is recording all the agent invocation. By recording all this agent invocation, it is able to provide a context for the agent, okay? Because this is quite important. When you have AI services, the AI services has a memory, of course, if you provide it, but the memory is very local to the single AI service. The single AI service doesn't know what happens with the other agentic iteration. So at this point, the chat memory is not enough anymore. You want the agentic scope to create automatically for you a context for the agent to know not only what the agent did before, but the whole agentic system did before. And then, of course, this thing is persistable, and you have a pluggable SPI to decide how to persist this agentic scope. So I can start also showing an example of this. Okay, so as you will see, we have both programmatic and the declarative API. Let's start with the programmatic one. So I have a different example here, which is quite similar to the things that I showed you before. I mean, here I have a CV generator. So I have a thing that takes the data of the user from a text file and generate a given CV, and then I have a CV tailor agent that adjusts the CV for that for the required job. Okay, so this is very, very similar to what you have seen before. By the way, this agent are here. So this is how an agent is defined in LangChain4j. You have a user message. You can also have a system message, of course. The additional thing is that you have this agent annotation. In this agent annotation, typically the one thing that you do is to provide a description of the agent. This is quite similar to what you have seen for tools. In a tool method, we wrote a description of what the tool does in order to make the LLM aware of how to use that tool and when, and we do the same here, but at a different level. Okay, we are saying with this thing what this agent is supposed to do. So one typical question is, what's the difference between the system message and what I wrote in this agent thing? The system message and the user message are the messages that goes to the service, to the LLM to invoke it. The agent description is the description of what that thing does. So it makes aware the other agent in the agentic system of what this thing can do. And so in this way, with the supervisor pattern, for instance, that we will see later, you make the other agent aware of what this agent can do and if and when to invoke it. Okay, so it's in general a good practice anyway to generate this thing. So this thing, again, same thing as before. It takes this life story, generate the CV, and then I have in this first example this CV tailor that takes the story and the instruction and generates a new CV. Okay. But what I'm saying, as I did before, is that no, sorry, this is the declarative example that I want to show you later. This is the programmatic one. Okay. Once again, I want to expose this service with a coherent way, in a single way. So this service take the life story of the user and the instruction to tailor it for the jobs at hand. And that's all it needs. And then you have in the agentic scope the different value for the states, and each and every agent knows how to access this data from the agentic scope and do its job. Okay, so let's give this a run. But in essence, what you will see is that it will call these two agents one after the other, doing this simple prompt chaining, taking the CV generated from the first agent, feeding with it the second agent together with the instruction to better improve the CV, and then you will obtain the result. Okay, so
but one of the difference between doing that with code is that the result you have is itself an agent. So you can take that agent and compose it in another bigger workflow, like the loop one, I think.
Okay, yes. So I have an example of this immediately after with the loop one. Okay. The example that I have here is still with the story creation example. What I'm doing here is that now not only have a style editor that adjusts the story for a given style, but I also have a style scorer that produces simply a score, a double, a number between 0 and 1 to say how good, how well the story fits the given style. Okay, so what this loop does is that it loops until I have an exit condition there. So until the style scorer says the story is good enough, or in my case, the score is bigger than 0.8, then you are good, and then you can exit and provide the story. And here you can see an example of what. No, sorry. Okay. Anyway, you can see an example of what Clement was saying in this sequence builder. You see, I'm creating a sequence of the creative writer, which is the simple agent that creates the story. But the second sub-agent of the sequence is this loop, which is on its own, not a single agent, but a complex agent made by the loop of the two, the scorer and the editor. Okay, so what this thing gives to you is that these patterns are building block that you can use to create more complex agent. Okay, and here you can see a few other features that the LangChain4j API provides for you. The agent, so far you have seen that all of the agents have a type, but it's not mandatory. In this case, I have an untyped agent. I'm not passing a class to that loop builder method. Meaning that I really don't mind what's the type of this thing. Normally, I do this for internal workflow. Okay, so this loop is not the thing that I expose to user. Is a thing that I use internally to improve the quality of the story. So what I expose to user is the story generator, and then in that point, I want to have a typed API with a clear value. Optionally, I can say, and again, I do this especially for internal workflow implementation. I can say, really, I don't want a type for this. It's not meaningful to me. I just want this thing to re-edit the story up until the score is satisfied.
So you're turning into a JavaScript developer, no type.
In this case, yes. If it's not exposed to the user, yes. I'm fine with this.
Do you mean that JavaScript should not be exposed to the user?
Well, yes. Okay, okay, this should be clear now. The output of the style scorer is that score variable, so it goes again in as a state variable in the agentic scope, and then the loop agent read that value produced by the style scorer from the agentic scope, and if the value is bigger than 0.8, that it exits the loop. Okay, and here you can see what Clement was mentioning before. The style review loop is by itself a complex workflow. It's not a single agent, but you are using as a normal agent, as a sub-agent of the sequence. Okay, so let me give you another example of this. Okay, I'm not going to run this, but just to make things clear, I have exactly the same thing as before. This is in the CV scope instead of the story creation scope, but this is exactly the same example. I have a scorer that decide if the CV is good enough, and it exits. I'm not going to run this, but it should be clear what's going on. Okay, and so far I used the programmatic API. But we also have a very similar API, I mean, with totally same feature, but based on annotation. So we have a declarative API. What you can do is something like this. I have a sequence here. I'm not writing any line of code. These two CV creator and CV tailor thing are exactly the same thing that you saw before, but I'm not creating the sequence programmatically. I'm just using that sequence agent annotation to create exactly the same thing as before, to create the sequence. And of course, you can do a loop with this. The loop also has the exit condition. The exit condition, to define an exit condition, you have to declare also a static method with that returns a Boolean to say if the condition is met or not. And for all other agents, you will see this pattern again. For instance, for the router, you will see that you use a different annotation to annotate a method to say if an agent should be invoked or not while doing routing, for instance.
One thing is that it's typed in the sense like the response of your CV reviewer is a complex object that you pass to your exit condition. So everything is typed. So it's not just string. It's not because it's declarative that you just have strings and errors can happen. Everything is typed correctly.
If you want, of course. I mean, the CV reviewer is producing. Let me show you the code. The CV reviewer is producing that CV review object. The CV review object goes again into the agentic scope. Is probably.
I think that's really important to mention, because like the CV reviewer parameter and the exit condition, I'm sure like most people are wondering like where does that come from, right? So yeah, let's expand on that a little more.
The object, you mean?
Yeah. So there was a parameter. So when you're using the programmatic API, you had the agentic scope context, then you had to pull everything out, right? In this case, where you were using the exit condition, you had a CV review, which was like automatically populated somehow, right?
Okay. So when I hit the CV reviewer, it doesn't return a simple string or double. It can eventually return this CV review object. And what I'm saying here is that the CV reviewer produces, sorry, it's here. the CV reviewer produces this output in a variable that is named CV review. And then I can use this exit condition because it's simply based on the name, right? So what happens here is that automatically what the framework does for you is taking from the agentic scope the CV review variable generated by the CV reviewer agent, passing it to this thing, and then you can use that value to decide if the score is good enough to exit the loop.
So if it were named CV Review 2, it wouldn't work, right?
No, yeah, because it's not the state
exactly,
variable.
Exactly. Yeah, I think just wanted to
okay,
clarify.
Yes. If you, of course, it's all based on the naming convention. So this thing has to have the same name of the output of the CV review because that's the name of the variable that is living inside the agentic scope. So this is really similar, exactly the same example as we saw in the programmatic way, but it's just declarative. I don't know if we have slides about the other pattern. Okay, yes. So let's see some other, the other two workflow pattern that I implemented in LangChain4j. So far, we saw the sequence, which is mostly used for prompt chaining. And we use the loop, which is used for what in the Anthropic paper was, I think, named reflection, meaning that the agent, by doing a loop, the agent is able to reflect on its own work and improve it. The third pattern that I have is the parallel one. Of course, in many cases, you want to run different agents in parallel and then aggregate their outcome. For instance, now I'm on the opposite part of the barricade, meaning that I'm no longer the applicant creating the CV, but I'm the company evaluating that CV. And of course, I have different people that has to review that CV with different, under different point of view. I have the HR reviewer, the manager, and the team member reviewer. And of course, these things are totally independent, meaning that I can launch them in parallel, which is what I'm doing now with this parallel agent. And then, of course, since I'm running these three things in parallel, then I need a way to aggregate the three results. And this is what you do with this method annotated with an output. Again, everything you see now with the declarative API, you have the programmatic counterpart in plain LangChain4j. This is also plain LangChain4j, by the way. What the Quarkus extensions gives you, in addition to this, is that it provides you with CDI capabilities. So what you can do by using the Quarkus extension is having this agent injected in your web service, for instance. So what I was saying is that you have these three agents, sub-agent, invoked independently because they do three different reviews. But then I want to aggregate them. So I have the review performed by the three agent. I create a feedback that is the concatenation of the two. And then I give to this thing a score that is the average of the score produced by the three agent. That's all. So it's just my business logic to aggregate what these three agents are doing.
One thing to add, these three agents, even in the previous example, could use different models. Gemini on one side, Quen on another side, a local one, in-process one. It's totally unrelated to how we assemble them. So remember that you can use different temperature, different everything.
Or it could be an A2A agent running somewhere else.
Yeah. Soon.
Okay, so I can have these three agents run in parallel. And again, what the Quarkus extension gives you in addition is that now I have this parallel reviewer, and I can simply inject my parallel reviewer here, and then I can use it in my main here, for instance. So maybe we can give a run to this. Let's actually, probably it's interesting to launch this in debug, so you can see when the output probably I have tons of breakpoints here. Okay, yeah, I don't. Okay. So what happens here is that I have these 3 agents that have been invoked. Now it's hitting this output function with the 3 review made by the 3 agent, and it's putting the value together. So the feedback is I don't know if you can read, but the feedback is the concatenation of the feedback of the 3 agent, and I want the score to be the average of the 3 score provided by the 3 agent. Okay, so this will be the final result. Okay, and I believe that with this score, I've been approved. Nice.
You're hired.
As a JavaScript developer.
Okay, I don't have slide for the latest pattern, but I want to show you quickly anyway. So here I have this little bit more complex example when I have a sequence. In this sequence, you see I'm composing many pattern again in different ways. So I have a sequence. The first part, the first agent of the sequence is the parallel reviewer that we have seen before. So it starts with the sequence goes to the parallel invokes the 3 agent in parallel, then it aggregates the result goes into this CV review variable, and then I have this second agent, which is actually the router, that takes the combined CV review, and it has 2 sub-agent, so it decides what to do based on the score provided by the parallel agent. So in my former example, the parallel agent, if you remember, produced a score, I believe, of 0.85, meaning that what happens is that I'm hitting this agent now. So the router is activating this one agent that organizes the interview with the candidate. Otherwise, if my score is below this threshold, I will activate this other agent that will simply email the candidate with a rejection email. Okay, so I'm really composing multiple kind of workflow to create a more complex agentic system. Okay.
Right. Stefano?
There any question about this, or maybe you want me to take
Mario had answer questions.
Okay. So
we have kind of a timing issue.
yeah. Sorry, but again, if you want to discuss this further, I will be around for the whole week. So feel free to get in touch. Go on. Sorry.
Yeah. I'll try to be quick and just to introduce what A2A is. There is a talk on Thursday if you want to join me for more details. But we got there. We have now an agentic system that Mario defined and so on. But there is another kind of problem, and is if those agents is remote or under control of some other organization, how to do that. So A2A is the answer to that, is a standard protocol of Linux Foundation, and as implementation in Python, JavaScript, Java, of course, I'm here for that. And Go is coming, and .NET is coming. So The very first thing is, well, just a quick question. Who knows about A2A? Have ever... Okay, you don't count. Okay, so basically, very first question, is an AI-related stuff? Kind of. Is more related to microservice, which are infused of AI. Could be, instead of AI-infused application, is AI-infused microservice. So what happened here is basically user request comes to a first agent that, just to use the slang that you can find when you come to A2A, is normally called a host agent or client agent. And this request can be spanned to other agent. How? There is a protocol of communication which is based, and we will see on different communication protocol, JSON RPC, gRPC, and the rest. And it sends a request. The answer from the other agent could be a message, but is not the typical way to work, because the typical way to work for A2A is answering with a task, because the idea is that those remote agents are long-running tasks, and those long-running tasks is normally AI-infused, but we will see that it could be also without AI. And those tasks can stream event of the answer and can be controlled. So basically what the specification define the protocol of communication between agent and the state machine for the task. So again, which are the core actors? The user, that is normally a human user, but not necessarily, of course. The client agent, as mentioned, and the remote agent called the server agent, normally. The A2A server. So the A2A server normally receives a request and processes the task. This task can be... it's too far. This task is processed with this state machine. But the very first point that we want to have for remote agent is a way to describe this agent. And we can see one. Do you have opened the one? While can you start the examples? Okay. While he is starting the examples, and so I can show you an agent card. The agent card is basically a JSON description of what agent can do, and is done by a description which is normally natural language description, and a set of capabilities and a set of skills. Difference between capabilities and skills. Capabilities is the capabilities in terms of protocol. So if that agent is able to stream message, for example, if it supports security, authorization, things like that. Okay, this one. And yes, capabilities is, so we have a name, a description, and a URL where you can find it, and you can find not only the agent card, but also where to communicate through HTTP or other protocols. As I said, we support out of the box JSON RPC over HTTP plus SSE, HTTP REST plus SSE, and gRPC. But the transport layer is pluggable, so a user can implement their own. Could be a local one, in-memory one, could be on HTTP stream, or things like that. Then we have the capabilities, so if we are able to stream, to push notification, and so on, and the input and output mode because it's natively multimodal. So here is text, but could be images, could be sound, could be video, whatever. And then the skills. The skills is what the agent declared to be able to do, and so how to select it. So is normally a natural description as a set of example. Here I haven't added, sorry, but there is another field that is pretty useful that is called documentation. And all the user think about documentation is user documentation, but looks is agent.md that you have to put in that documentation so another LLM can better understand how to use it. And can you return?
One thing, Stefano, that description you have here is equivalent to the description you have in agent in code. So.
See.
Okay, so in the A2A protocol, we have the agent card, the concept of the task. So the task is the long-running task normally that can answer with event. There is the message that is normally what start the communication and could be used also for synchronous response added in a latest version before we event it. There is part and artifact which are the final answer, and it's important to note there is parts because you can answer in a fully multimodal way. So in an artifact I can have different parts that could be both text and images. This is the state machine. I'm not going too far on that because it's a pretty straightforward state machine. The only thing I want to make you note, there is also input required and out required state for the task, because an agent could answer you instead of giving you an answer, asking you for other inputs. And this is a key point in A2A because it's considered as having always a human or another agent in the loop. So you can have a very long running tasks. So basically the big difference between the agent as defined by A2A and the tools as defined by MCP is here, the ability to take a long-running task and to get the goal, cycling and asking for other input and collaborate with other agents, and not just having a well-defined input-output mechanism like a tools is. So, other important concepts, I want to mention authentication and authorization is not written here, but is important. Classical enterprise level feature, so you have authentication as a primary point and a very important part of the protocol, and the same is the authorization. So you can define different level of authorization in agents. And then extensions. I think extensions is an important point to touch on A2A protocol because the protocol is pretty young, and in this context of AI, things are changing so fast that the steering committee decided to don't put everything we can in the specification by itself, but create the concept of extension. And those are not extension on the code, but extension on the specification. So you can use an A2A compliant set of services and provide your own or a well-known extension specification. The most notable example and very recently released by Google at the moment is AP2 for agent payment protocol, which model throughout A2A a payment delegated to agent. So I want to buy my shoes and I want that the agent find the best price and provide all the transaction basically what OpenAI is doing inside of ChatGPT, but as a protocol. And most and even more interesting is X402. X402 is, let's start from the name again, and that is pretty cool. HTTP 402 is an error that is there since the version of HTTP 1.0.
Yep.
And you know what does it mean? Probably not, because no one is using, but it means payment requirement. So they are reusing this standard error to provide a payment requirement. And this is a protocol, again, on payment, but on micropayment between agents to create an economy of agent. So I want to use your agent, and this agent will cost something. The protocol is coming from Coinbase, so cryptocurrency world, but still is applicable to any other thing. So now I have a very quick example, if we can run it. Stay on the slide just a second that I explain what we are going to say. So we have a front end, an host agent or client agent that span the creation of an ex post to different agents, and those are written, one in Python, one in Java, and one in JavaScript. Because having a different SDK in a very well-defined standard permit us to make them communicate. And this probably is something that more and more we will see in our job or day-by-day job, to make communicating different agents written in different languages, and for which we don't have direct control. That is another important point. The protocol and the standard insist a lot on opacity of agents, because you don't need to know how things are done, but you need to know what they are doing, and so what are skills provided. So let's run this agent, this set of example. Mario started the 3 agents. Okay, this is the, okay, and let's write a post on X. And if Gemini will assist us, we will have the post. Okay, here is what is happening. I'm calling the first agent, that is content planner agent, the Python one, and he is working. Hopefully he's working. Okay, it worked. And he gave the first response to the host, then we'll call the second agent and get there the answer, and finally the JavaScript agent, that is the editor agent. The very last bit that would be great to show you is that because of the standard, as soon as the JavaScript agent will answer, okay, but the great part okay, the great part of the standard is that having a standard, we can swap one of those agents, and so you have the honor to kill JavaScript and swap with a Java agent that is doing the same. Okay. And we will see the agent card that is exactly the same, just a bumped version, just to see that is different.
Content editor 1, right?
Content editor, Maven Quarkus dev.
Okay. I can go.
You have the example, and if you stay until the end, you have the QR code to look at the example and run yourself. There is also a blog post on this example from my colleague Farah. You can read the full blog post, which explains very well. It's on Quarkus blog.
Yeah, what you didn't say is that Quarkus has both, you can implement your your A2A agent using Quarkus, as you did, but you can also invoke your A2A agent from Quarkus. It's actually completely hidden. You just, like MCP, you import it as an A2A agent and voila.
Yeah. The Quarkus client side is already like that. The SDK provide the Quarkus as a referential implementation. We have also Jakarta EE1, and we know that someone else is working on server side, but in the end is an AI service. If you look at the example for the Quarkus agent, we have just the executor, that is your business logic in A2A, that just call an AI service.
Should be up.
Okay.
Or do you want
show
to
the agent
this?
card, just the agent card.
Okay.
Okay, it's just 2.0.0 and is all the same because I implemented the same. And if Mario run the same question, it will work as before, but not using JavaScript. So we swapped an agent because it's more stable, is a better language, and so on and so on. Then we can just launch it, but we can move on because the time is...
Okay, yeah, I'm not going to trigger this.
Okay, no.
To save a bit of time.
Yeah, okay.
Yes, yeah, we are just replace it.
Yeah, but you can try it. It works.
Okay. Yes, what
on the slide? Oh, what do you want to...
No, I just want to reinforce the thing that with Quarkus you have both the possibility to create your own A2A server. What you have on the LangChain4j side is the client part, so you can still programmatically create your agent that this time is running remotely on an A2A server, and of course you can mix local and remote agent inside the same workflow.
And you can compose them using
exactly, yes, you can mix them.
The agent server, the A2A server, could be a set of agents that Mario implemented. So it doesn't need to be a single class or whatever. Could start a set of agents, and there is many example with many frameworks in Python, for example, Crew AI and others, and the same is doable in Java now through Quarkus.
All right, so last part, we're now going to view another pattern, which is not workflow. This time, we're going to increase the level of autonomy of the agent, so we trust AI, and we tell him, okay, that's what I want to do. Here are all the agents you have access to. Do it.
Where is the clicker? Okay.
We lost the clicker.
AI will find it.
It is. Okay.
Oh, okay.
Okay, so do you want to...
No, go ahead.
Okay. So what the next level of autonomy that I implemented is that I don't want only the agent, the single agent, to be based on an LLM, but I also want to coordinate them in an agentic way. Okay, so the difference with this pattern, between this pattern and all the one that you have seen before, is that with workflow pattern you have a programmatic way to put agents together. You would create a sequence, you create a loop, you create a router, or you run them in parallel, but they are all executed in a fixed, in a well-established way. And to be honest, if you have a chance to do so, do so. Meaning that you want to have an agentic supervisor only when you really need it, only when you don't know in advance which agent you need to call and you want the LLM to decide. Okay, so what this thing is doing is that it is provided with a set of sub-agents, exactly in the same way as you did for the sequence, for instance, or for the parallel workflow. But this time, this agent ABC are not going to be called in sequence, but it's up to the supervisor to decide which agent to call and with which arguments.
Which means that the description you give to your agents, either in the A2A card or inside your agent annotation, are very, very important, because that's how the supervisor will deduce which agent need to be called and which parameter and so on.
Exactly. So just to be clear, so far in the former example, I gave a description to the agent, but it was not really used. This was just for informative reason, but you define, you want to run agent A and then B and then C. Okay. Now that description is really important, because it's the one thing that allows the supervisor to decide which agent it needs to call. What the supervisor does is create a sequence of this agent invocation object. Okay. An agent invocation is simply the name of an agent together with the arguments that you want to use to invoke the agent. So I guess I have, okay. So this is what the planner agent internal, that is internal to the supervisor pattern, how it is defined. So the first thing you can notice is that it is returning that agent invocation record, which again is the specification of how to invoke an agent, okay? And then the important thing is that I have a definition of done. So at some point, the supervisor needs to figure out, okay, I've completed the task requested by the user. So in this case, what happens is that it generates a special agent invocation that is called done. And in this way, the system knows that the execution could be finished, interrupted. Okay. What happens about the sub-agents? What we do is that I simply do a concatenation of the description of the whole agent. So I pass to this in that agent placeholder. I pass a JSON concatenation of the description of the different available agents. So I say agent 1 does this and that, and takes this argument, and then agent 2, and then agent 3. Okay. So I'm passing this agent in this way to the planner, and the planner is deciding which agent to invoke. And then yes, and then the supervisor is fed with all these information that are the available agent, the user request, the last generated response. You will see now why it is useful, and you have an optional context that you can add to the prompt of the planner to give it even more context based on your use case. Okay, so what happens in reality is that I have this planner that is using the information contained in the agentic scope, which once again is the story of all the agent invocation, and it generated one after the other this agent invocation. This agent invocation can be a done invocation, meaning that the process is finished, or it can be an actual agent invocation. If it is an actual agent invocation, the agent result goes into the agentic scope as well, and the planner using it to generate the next agent invocation. So this means that we don't have a situation where the whole planning is generated up front. We tried it, and to be honest, it didn't work that well. What it works for us is that it generates an invocation after the other, and all invocation is generated taking count of all what happened before. This worked very well, okay? At some point, the planner decides, okay, I'm done, so it produces this special agent invocation that is called done, and in the done invocation, it also generates a summary of all the action taken. What happens next is that the user input, the summary of the action summary, and the very latest response generated by the very latest invoked agent are passed to another agent, which is this response scorer. Because what I saw is that there are two different possible use cases, okay? Think about it. If you want this agent concatenation to create a story like we have seen before with the creative writer and then the style editor and then the audience editor, the supervisor will call them one after the other, and then at that point it decides that it's done. But what you are really interested in is not the story of the agent that had been called. You are really interested in the final output, in the latest response. Okay. In another example, it may, and you will see them later. In another example, you can have a sequence of bank transaction generated by the supervisor agent. In that case, you probably want a summary of all the action that have been taken. The latest response is not enough, okay? But even now, we don't know in advance. So what I did is that I have this response scorer that is passed with the input and the two possible responses. It gives us scores to both responses to decide which one fits better the user request and decide which one of the two it has to be returned. Okay, and you can eventually skip this stage if you know in advance that you want the summary of the action. You can skip optionally this response scorer stage and say to the supervisor agent, always return the summary. So I have an example here. In this case, I have these three agents. I have an agent that withdraw money from a bank account in USD, and a credit agent that does credit money on a bank account. And I have an exchange agent that simply decide the exchange rate between two currencies. Okay, so what I'm saying here is that okay, I have my functional bank and I have two accounts in this bank, and then I created these three agents, and then I'm creating the supervisor passing these three agents as sub-agent. Okay, this is once again, this is exactly what you do to the sequence, with the difference that this time these are the three agents available to the supervisor, that they don't have to be called in sequence. They don't have to be the call just once or more than once. It's up to the supervisor to decide. So what I'm saying here, okay, it's transfer 100 euro from my account to Chemist One. And this is the reply. Again, the reply, okay, you owe me a beer. And then the reply, as you can see, it's not only the latest transaction. In this case, you really want a summary of all the action taken. And what are these action taken? So, okay, I don't have the slide here, but I can show you the example. Okay. So, okay, the bank tool is simply this tool that credit money to a bank account that withdraw money, and then I have the exchange tool. Okay, I have some exchange rated that are coded here, but normally, of course, you can put in the tool a REST invocation to a service, external service that gives you the given current exchange rate. And I'm saying, okay, this times I'm giving 100 euro to Georgios, but
money everywhere.
Yeah, everywhere. Okay, so I'm creating this thing. This time, okay, I'm using the declarative API, so I have my three agent here, and then I have my supervisor configured with this three agent. Okay,
don't look at that .at v thing. That doesn't. You don't need it.
Yeah, but you see in the previous one, you have also the output strategy. So you said explicitly that you want the summary in that case.
Yes, exactly. Okay, so there is something wrong.
Yeah, 8080 is used.
Maybe stop.
You can use Guardrails directly on every agent you have. So the import and output Guardrail will work out of the box. However, we don't have Guardrail yet on the supervisor itself. So it's something we want to add.
Good point, yes.
Yes. So, yeah. Well, only use that level of autonomy if you know, if you trust your model. Otherwise, Mario is out of money.
So let me check if I can find those.
I think like the recommendation from everybody, not just us, right, is like use totally autonomous systems only if it's absolutely necessary. Like the less autonomy you give them, the better.
Yeah, so only use that if you want your system to adapt to really unknowns. And in that case, yes. And you can combine the agents that we have in our fleet of agents can be implemented using workflow or something different. So use that level of autonomy only maybe on the first layer and then use things where you control a little bit more everything. Otherwise, yeah, bad things can happen.
Okay.
It's the very beginning. Did it run?
What I wanted to show is, it of course transfer the money from my
Did it
account.
cost you more on
with some
OpenAI
rounding
than you gave us?
this time, okay? But what's interesting are the sequence of the agent invocation that have been generated by the supervisor, okay? So of course I'm saying that I want to transfer 100 euros, but if you read the description of the agent, it says that all these accounts are in USD. So the supervisor knows that the first thing it has to do, or decides that the first thing it has to do is to call the exchange agent, converting 100 from euro to USD. Okay, so this is the first agent invocation that it generates, and then there will be a second one when it taking. Should be 115. It's 114.999 euros from my bank account, and then I have a third agent invocation when it's crediting the same amount of money to Georgios' account, and then I have a fourth agent invocation. That is the special invocation that says done, which is the last one with a recap of the action it took. Okay, so this is what this supervisor is doing. Again, I'm not programmatically saying to the supervisor, do this, do that. It is the supervisor itself that is generating alone this sequence of invocation and calling the agent accordingly.
Let's go back to the slide and conclude very quickly. All right, end of the session. We still have 4 minutes. It's amazing. We promised it. So here are the link to the slides and the code. We have way more demos in the code, so feel free to go there, run them. All our examples have local versions where you can use a llama and run them. Maybe not all, I'm not sure about the A2A, but the large majority as examples where you can run them locally with local model if you want to. Well, get a beefy machine first.
Good GPU.
Yeah, with a large GPU. We didn't see everything. We have seen a couple of things, but we have not seen the workflow SPI, so you can actually implement your own workflow API on top of that. We didn't see really resilience. We didn't see the guardrail on the agents themselves. We didn't see the programmatic agent, human in the loop, so that's all things we also have. Some stuff need to be reworked a little bit, but we have seen a lot of things. If you want to see more, We have a lot of talks about Quarkus and Quarkus on Chain4j at Devox. I think something like 18 or something like that. So just this afternoon, we have a lab where we are going, where you are going to use what we just show you in a real system, so workflows and things like that, and A2A. We have the talk I mentioned earlier about our stories and failures we made, which is on Wednesday. It's from AI infused to agentic enterprise framework. For people not wanting AI, we also have tons of pure Quarkus one, like Quarkus, the bold, the broken, and the burned, from Georgios and Guillaume, explaining all the failures we made in the last 7 years of building Quarkus. So yeah, and you can see all these talks by scanning that. If you go back, and we have 2 minutes, 23 seconds for questions. Woo! We made it fit.
Okay, if you don't have question, of course, we are around for the rest of the week.
Do we have a question?
There's a question?
Yeah.
Wait.
So, okay, go on.
Wait. Well, we are there till the end of the week. You can, we have tons of talks, so you can still attend the other one, or we will be around the Red Hat booth.
Hey, thank you very much for the talk. Very interesting. So does the supervisor pattern have the risk of just going in an infinite loop?
No.
Because the loop pattern had these max iterations, right? So what about the supervisor? So
what you have at the moment, the only way to tune it is that you optionally have parameter to say, I want to have a maximum number of agent invocation. For instance, you can say, I want at most 10 agent invocation, and then regardless of what you have done, you have to stop. Okay, so this is the first control that you have. I could add an exit condition as you have for the loop pattern. This should be pretty easy. So this could be interesting indeed. So you can have a way to say, okay, if this value is above this threshold, then I want to exit.
It's one of the reasons why we don't use function calling to call our agents, because we will be out of control. That's why we are generating this agent invocation, and we are in control. We know exactly what we call, when, how many times, and things like that. So that gives you a level of observability, but also a level of control, which avoid you completely derailing.
Right. Thank you.
But in reality, yes. If you don't set an exit condition, if you don't set a max, you can end up in an endless agent invocation. Yes.
And Google and OpenAI will be very happy.
Yes.
Thanks.
All right, we are done. Thank you again. Thank you for attending. And yeah, if you have any follow-up questions, well, we have tons of talks, or see us on the Red Hat booth. We will be around. Thank you.
Thank you.